Before I jump directly into the talk, I'm going to give a little bit of outline about what I'm going to talk today. I'm going to start with what are orphan wells, and followed by what kind of data resources out there, historical well data, and other types of data, and what is history about, a little bit of history about aerial imagery program in the United States, and georeferencing techniques, and followed by a field survey, which is a case study, and showing some results. What is an orphan well? The term itself is actually varied by state. Each state has their own definition. Most of them has their own definition about orphan wells. I'm going to give a little definition of what an orphan well would be. It's a well that's may or may not be in the database, but they don't know about the history about if it's drilled or if it's existed or not. There, according to IOGCC, there's orphan wells are defined as documented and undocumented. A documented means they have a record of the well being drilled, and it's been abandoned after that. And undocumented means that there's no record of well being drilled, and at some point someone finds the well and, oh yeah, there's a well here. So why is this orphan wells so relevant to the current scenario? It's because improperly plugged or unplugged orphan wells may pose a significant environmental risk or threat to the surrounding environment in the way of methane emissions or groundwater contamination, and in some cases, which we have heard recently as well, last year, well communication incidents. A good example is in the Greene County in Pennsylvania that happened last year. So this program of undocumented orphan wells through NETL is funded by BIL. It's a 5-year program. We're currently in the second year. The main goals of this program is to identify and characterize orphan wells across the United States, maintain a database of that, make it complete, and rank the wells based on their environmental risk and hazards. And finally, plug, remediate, and reclaim these wells. So before I jump into a more detailed topic, I'm going to start with what kind of data resources out there and what kind of scientific approaches are being followed in the current scenario. So the state database, there are like two main sources of well data that can be retrieved. One through the state databases for public access. You can do it private as well, but I'm talking in a case of public access. The main one is through the state databases, which they collect, maintain a database of well records based on the permits and etc. And the second is the historical USGS topographic maps. That's one of the good resources as well. That's not widely known to the public, but it's existed. And the other scientific approaches is through aerial magnetic surveys and LiDAR surveys. So I'm going to give a little introduction about the state databases. As I said earlier, these state databases maintain records of through oil and gas permits and production and drilling records, and they maintain API numbers as well as the well status in some cases. USGS fortunately maintains a website that takes you to each state or most of the states' databases, if existed. And the second one is the historical USGS topo maps. As you can see on the right, there's one of the good examples of a historical topo maps. And let me point there. So you can see when you look closely at the map, there's like small circles over there. So these are the circles that handprinted by USGS back in between 1940s to 1990s. They field checked these wells using historical USGS. It's not historical at the time, but USGS has taken pictures, aerial photos at the time in 1950s, and they went to the field and did field verification. So these circles are actually field checked by USGS. And unfortunately, due to the higher expensive estimates by today's standards, this kind of approach has been discontinued moving into the 2000s. Another scientific approach, the first scientific approach that NETL has followed in the recent years, dating as back as 2015, is the aerial magnetic surveys. So my good colleague Jim Sams has been very well active in that kind of area as well. So basically, NETL flew a helicopter on Hillman State Park and a few other areas of interest around Pennsylvania and in South as well. They flew a high-sensitive aerial magnetic sensor that basically sends the electromagnetic pulse onto the ground, and whatever bounces back to the sensor is essentially from any kind of metal. It reacts to the magnetic pulse. So this is an example picture of a Hillman State Park in Pennsylvania, north of Pittsburgh, but actually west of Pittsburgh. And you can see the hot spots on this map here. It's a magnetic bump map, and you can see the hot spots over here. These are presumably wells, and we actually did a field check back in 2015 to find for these magnetic hotspots, and turned out to be their wells. And these are and they're not all of them were in the database as well at the time. And when you go back to the Pennsylvania state database, there's only 250,000 of wells that's been in the database. But according to the literature history and other studies, it's reported that there is somewhere between 1 million and 2 million wells that's been drilled in the Pennsylvania alone. So there's this kind of surveys that kind of fills the gaps between what's data available out there and what needs to be done. And another approach, which is much more recent as well, is LiDAR, using LiDAR as a technology to find wells. So the basic workflow of the LiDAR technology is we get LiDAR data, point cloud data, and we process that with respect to the ground reflection points or ground points, and we convert that to a digital elevation model, or DEM, and we take a slope of DEM to get a nice topographic map of the LiDAR. And so this is an example picture of a LiDAR map we have processed for Stonewall-Jackson Lake area in West Virginia. If you zoom in to the top right area of the image of the map, you can see some well pads over there, and some of them are in the database and some are not. And this is a closer picture, so you can see almost all the points are in the database. But and at the same time, the points in red, which are unknown wells, and the point in green, which are historically gas production wells, they're not exactly on the well pad. Their geographical information is quietly offset. When you go into the field looking for a well, if you don't find a well, then that's going to be a waste of time. So LiDAR can be used as a tool in that aspect as well, for navigation through the dense wooded areas, as well as wells that are not accurately represented in the database. So it sounds all pretty good. Why am I talking about right now? Because we have all these technologies that's available right now out there, and we can do more about it. So why am I looking for something else out there? It's because the main interest is the well database available from the state resources are incomplete, as I have mentioned a few examples earlier. And the USGS topo maps, even though they have done field checking back in the day, they didn't have any accurate GIS technologies or GPS technologies at the time to pinpoint the well locations on the map. So they have to manually draw these circles on the topo map, which have an offset of a few meters, actually many meters. And these circles itself are in 10 meters radius. So that's going to have an internal offset as well. So they're pretty off when we check in the field with the using current technologies. So, and at the same time, the aerial magnetic surveys and the LiDAR surveys are expensive. So if you are working in a government lab and you don't have a lot of money, so you have to look for other ways as well to find these wells. And the main drawback of the aerial magnetic surveys are there could be noise induced because of other material debris around the field, especially if the field has gone through a lot of land use and land cover changes. And same case with the LiDAR, where when there is a land change or some of the activities going on to the land, there could be a change in the LiDAR topography as well, And in a particular case with the LiDAR is you can the older wells especially they never had a big well pad built at the time. So the older wells are kind of hard to be visible on the LiDAR data. So this is a good example of Olean, New York that we have done study field surveys back in 2022 and 2021. So on the left, it's a USGS topo map for the property we were interested in, and on the right is the magnetic bump map of the same property that's been taken using a drone. So when I say drone, it should have a much more filtered data or much more fine data. But as you can see on this map, it's pretty hard to define. When you see the helicopter survey map from Hillman State Park, it's much more finer than this one. But what went wrong here? So turns out when we went to the field, there's a lot of metal debris that are laying around all over the property. It's not because the operators left it there like that, but it's mainly because there was when these wells were drilled back in 1920s to 1950s. After that, in late 1970s, there was a huge tree logging activity that's been taking place on the same property. So when I say tree logging activities, they pulled everything on the way. They came across the way. So we had all this metal debris lying around the field. So that resulted in like very noisy aerodynamic survey. And on the left, you can see there's so many wells on this property. That's count to about 200 wells alone in this property from the USGS topo map. Whereas from the state database, there's only 26 wells. So there's a huge gap in what's noted in the states and what's on the ground. So we have seen the same case with the LiDAR as well. When we process the state LiDAR data with a lower cell resolution, we couldn't find any well pads over there. Of course, you can see some on the northeast, but mostly on the property area, we couldn't find any well pads over there. But we could see the trails clearly on the LiDAR data. It could be due to the logging trucks use the same haul roads that that were used to drill the wells. So that's why they were not pretty much disturbed. So what could be done here? So we have all these approaches and nothing would work in Olean. So we had to look for something else. So that something else was a historic aerial photo. It's kind of like digital twin that Dr. Johnson was talking about earlier in the keynote speak. So the historic aerial photos is not something new. So that's been done by USGS back in the day, and they have done a pretty good job at it, making the maps, topographic maps, and having the wells located on the maps. But they didn't have access to the GIS technologies that we have nowadays. So imagine if they had the same access back in the day, they would have done even better job not better job like in the terms of like having better accuracy in the maps with respect to what's on the ground. So that's why we are going to take those historical aerial photos and combine them with the modern GIS technology and have a better representation of what's on the ground. And so before I jump deeply into the historical aerial photos and georeferencing, I'm going to start with what's the history about the aerial imagery program in the United States. So it's actually began back dating as back as 1930s, 1920s as well. So 1930s, and it was mainly carried out by 3 agencies: Farm Services, Forest Services, and Geological Survey. So as I said, the USGS topo maps were field verified by the USGS, photos taken by USGS in 1950s. In terms of storage, you can access the USGS aerial photos from Earth Explorer, even though the quality isn't great. You can actually request for high scans as well. And in most cases, in some cases, you'll find the USDA or Farm Services back in the day, these photos from state databases and archives, state archives. And in almost all scenarios, you can find all these photos from National Archives. So that's like one platform to find everything. So this is an example of a historical aerial photo. On the left is from our area of interest in Olean, New York, which is taken by USDA in 1952. And on the right is an aerial photo taken by USDA as well in 1939, covering a part of our project area in Daniel Boone National Forest in Kentucky. As you can see from this picture, there's so much tree openings, those features that represent a well pad. So these are in any given scenario, these are kind of features we are looking for to find for wells using aerial photos. So we use these aerial photos and combine with GIS techniques called georeferencing. So we georeference. It's a technique that connects existing known features from this there. So it's a technique that connects the known features, such as a corner of a building, like here, or road intersections or trail intersections in this case, to a geographically referenced layer or image or base map. So these known features are commonly known as ground control points or GCPs. And the more GCPs you have, the more accurate GCPs you have, the more accurate your georeferencing technique will be, which means that leads to low RNS error. And so since there is no flight data associated with this, it's pretty hard to auto-rectify as well. There are like different techniques you can apply in georeferencing, one being first order and second order and third order. There are other techniques as well, but these are the mostly used techniques in GIS field. The first order polynomial only requires 3 GCPs, so it's not the accurate one. And the second order requires a minimum of 6 GCPs, and third order requires a minimum of 10 GCPs. So the higher order you go, the more GCPs you want. At the same time, it's pretty time consuming as well. So you need to find a sweet spot between the first order and second order and third order, which is actually second order. Only requires 6 GCPs at least, and it's easier to it's time saving as well compared to the third order polynomial transformations. So one of the techniques we found with respect to georeferencing is the smaller the size of image, it's better it would provide a better accuracy in the georeferencing technique. So what we did is we took a bigger image and we cropped it to our product area, and we proceeded with the georeferencing using second order polynomial for that area, and we found about 11 control points in that area that led us to close to 3 meters accuracy. And we went ahead and digitized the center well pad of each center point of each well pad we identified, and we used those points for field verification at a later date. when you so the red points are the ones we digitized uh, using GIS softwares uh, to field verification, and the yellow ones are the ones we found in the field using these points as a reference. And this is a field survey equipment we carried with us. We used a backpack magnetometer, took that with us because we knew that area was heavily subjected to tree logging activities. So in most cases, the wells casing was cut off or buried in cases like that. And so we needed a walking backpack magnetometer to find these kind of wells as well. And we also carried a high resolution GPS to record the high resolution geographical information. And we carried remote methane leak detectors and the high flow sampler to measure methane leak rates. Coming back to the results, we digitized about 94 well pads from the aerial photo, and we found almost all the actually every well pad digitized from the aerial photo on the surface, on the ground. So we were able to find all the 94 wells, but the most interesting thing is the 55 of the 94 well pads, 94 points we found in the field. 55 of them were within 50 meters of the well pad we digitized on the georeferenced image. So this technique shows it could work as an alternative for other approaches that won't work in cases like Olean, and it's pretty cheap. That I conclude.